So brief a summary cannot convey the true spirit and intention of scientific probing of the past, any more than the spirit of history is conveyed by a table of dates. We seek the truth, but if some voice told us that a few years more we would see the end of our journey, that the clouds of uncertainty would be dispersed, and that we should perceive the whole truth about the physical universe, the tiding would be by no means joyful. In science and in religion, the truth shines ahead as a beacon showing us the path. We do not ask to attain it. It is better far that we be permitted to seek. Arthur S. Eddington, from Science and the Unseen World. With these words, written later in his life and in reference to relating the paths of stellar and human evolution, we see deep insight into one of the guiding values of the author's approach, not just to science, but also to all the important aspects of his life, that of the centrality of seeking. Through the readings of the writings and speeches of George Fox and Sylvanus P. Thompson, Arthur Eddington would fashion a profoundly radical understanding of how the mystic, both in science and faith, would make progress towards truth. Thompson would write about science, quote, "What the scientific inquirer does is to hazard a number of hypotheses, some of them quite profitable, others quite improbable, and to test them one by one to see which is right or which of them is nearest the truth. For every hypothesis that turns out to be correct, he may have to frame a score that prove themselves invalid. Persons who do not understand this mode of arriving at the truth often regard this as a very shaky procedure and condemn it as trying to arrive at the truth by means of error. It is better to make wrong guesses than to be in such a muddled state of mind as to be able to guess at all." End quote. Similarly, Thompson wrote with respect to spiritual matters, quote, "The craving for certitude is not in all respects a sign of spiritual health." End quote. And so it was, on this foundation, that Eddington would forge an identity that integrated his scientific and spiritual pursuits in a completely self-consistent way. This value of seeking would allow Eddington to, in the words of Matthew Stanley, quote, "found a philosophical bridge to span the disciplines, where the religious scientist was reassured not by the fingerprint of God in the world, but rather by an outlook that brought all forms of truth thinking together." End quote. In Eddington's words, the valence values of science and religion that led to seeking, quote, "points the way by which the conception of man as an element in moral and spiritual order can be dovetailed into the conception of man as the plaything of the forces of the material world." End quote. Continuing, Eddington would write, quote, "The desire for truth, so prominent in linked science, a reaching out of the spirit from its isolation to something beyond, a response to beauty in nature and art, an inner light of conviction and guidance, are these as much a part of our being as our sensitivity to sense impressions?" End quote. From these words, among many others, we can see that for Eddington, as he began his scientific career, and ever more so afterwards, it was this ability to reach out, to explore, to further the process of seeking that was the most important aspect for good scientific work and good theological work. In his view, a good hypothesis was not good merely because it described a physical system approximately accurately, or that it created a deeper understanding of the divine. It was good also because it created new paths of exploration. Again in his words, quote, "The spirit of seeking which animates us refuses to regard any kind of creed as its goal. Rather, it is actually an aid in the search for knowledge to understand the nature of knowledge which we seek." End quote. For Eddington, science was more about the process than the endpoint, and as such, he was able to take bold steps in proposing ideas that might seem initially unfounded as part of his investigations. Instead of seeking the selection of a model as a commitment to a solid physical position or capital T truth, He saw it as a path of speculation and exploration that offered the chance to open up new vistas and further avenues of discovery. And while this approach would put him at odds with a number of his colleagues in the British astrophysical community, it would also pay enormous dividends in understanding the very processes that unfold around us throughout the cosmos. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 49.2, Supplemental-Arthur, Stanley, Eddington, A Seeker's Journey. As we left off in our last episode, Eddington had finished his Bachelor of Arts at Cambridge University with the distinction of having been named the best mathematics students in his second year enrolled. This achievement, roughly equivalent to a master's degree in the United States today, along with his strong background in practical physics from Manchester, had landed him a position as one of the two chief assistants at the Royal Observatory in Greenwich. He would remain at the observatory for the next 7 years, doing some observational work, but mostly focusing on using data to address a number of research problems. From the time of Flamsteed and the observatory's founding, its primary responsibility had been to provide accurate charts of the positions of various objects in the sky for the British Admiralty, as well as helping to establish the locations of various places in the wider British Empire to as high a degree of accuracy as possible in order to also aid in navigation. While these were the primary missions of the institution, they did leave plenty of time left over for its staff to take up research projects related to the main tasks, and so it was that Eddington came to be involved in the problem of proper motions of stars in the celestial sphere. As you may recall, it was Halley who discovered the fact that the stars were not fixed on the celestial sphere, and that they had what was known as a proper motion, or a change in their positional coordinates on the celestial sphere, i.e. their right ascension and declination. William Herschel, among others, used increasingly accurate telescopic observations to examine these motions in greater detail and found evidence that suggested that the sun had a specific motion in a given direction through space. At the time, there wasn't a very good model of the galaxy, and so that motion was not well understood. By the time of the early 1900s, this problem was still an area of active research, with the primary principles in the field being someone by the name of J.C. Kapteyn at Groningen University and Carl Schwarzschild at Göttingen. The two men had suggested slightly different approaches to modeling the data mathematically, with Kapteyn putting forward the idea that there were actually two motions that needed to be accounted for, one associated with the sun's motion and the other corresponding to the bulk motion of the stars in the solar neighborhood. Schwarzschild, on the other hand, proposed an alternative analysis that used a more complicated mathematical model that suggested that there was really only one motion that was required, that being the motion of the sun, and this model was known as the ellipsoidal model. Eddington, using data collected as part of the ongoing Royal Observatory efforts to create ever more accurate stellar charts that characterize the proper motion with unparalleled accuracy, developed a method of statistical analysis that led him to support Kapteyn's two-stream model. This was really an impressive piece of work, and it garnered him immediate attention and began to create a reputation for him as a mathematical astronomer of rather significant ability. Unfortunately, due to the continuing lack of a good understanding of either the size or the shape of the galaxy, as well as the Sun's position in it, further progress was more or less stymied until the work of Leavitt and Shapley. While further developments would bear out Kapteyn's model, it wouldn't be until the work of Jan Oort that we would fully understand the various motions of the Sun and the stars around the galactic center. However, it was Eddington's work in this area, as we said, that really did establish him as a rising star among mathematical astrophysicists in the various circles both in England and throughout Europe. His mathematical reputation, however, was also further cemented when he developed a new statistical method for deriving the orbit of the asteroid 433 Eros from measurements of parallax. Eros is a near-Earth asteroid that orbits the Sun in a way that its eccentricity actually brings it inside of the orbit of Mars. It's sort of an Earth-approaching asteroid, as they sometimes call it. As such, it is possible to use measurements taken of the position of the asteroid shortly after sunset, and then again shortly before sunrise on that same day, or crossing midnight as it were, to create a baseline with which to measure a parallax shift and thus calculate a distance. However, during the few hours between when these observations are taken, the asteroid's observed position will also change slightly due to its inherent orbital motion. And so it becomes an issue to separate the changes due to the motion of the asteroid from the changes due to measuring that parallax shift in order to find the distance of the asteroid to the Earth. Eddington's model allowed this to be done in a more accurate fashion than previously was possible, and for his work he was awarded the prestigious Smith Prize by the Royal Astronomical Society, as well as being elected as a permanent fellowship, or a permanent fellow I should say, to Trinity College at Cambridge. Thus, by 1907, 2 years after assuming the position at the Royal Observatory, he was very well established in the astronomical community. Over the course of the next 5 years, Eddington would be involved in this sort of work associated with matters of applying physical models and mathematical techniques to questions in the field of positional astronomy. In the papers that he wrote published during this time, one can see both his mathematical acumen in developing extraordinarily elegant approaches to complex and difficult mathematical methods, and also his willingness to, in a sense, take a few risks in making various physical assumptions to see where they might lead in creating a model that better represented the data being collected. It was in this way that Eddington would first come up against another giant of British astrophysics for the first time, that individual being James Jeans, about whom we will have much more to say in due time. Jeans objected in a paper that he gave at the Royal Astronomical Society to one of Eddington's assumptions when he had been analyzing the data from the Royal Observatory's latest proper motion catalogue. And Jeans had argued that such assumptions shouldn't be made without strict mathematical justification. It would be the beginning of a long dialogue about the proper way in which a good scientist practices inquiry that would run for a number of years. In 1909, Eddington was selected to head up an expedition to the island of Malta in the Mediterranean Sea to establish with greater accuracy the exact latitude and longitude of the British naval station there. A discrepancy had been noted between two earlier observations that would lead to the possibility of a navigational error that could result in a ship running aground. And so the Royal Observatory sent Eddington and an assistant to make a new set of measurements to establish the location with as much accuracy as possible for comparison. Taking measurements over the course of about a month, Eddington was able to confirm one of the previous measurements as well as reduce the positional uncertainty to about 0.01 seconds of arc. This showed that Eddington was a careful and accurate astronomical observer, and it honed his skills of setting up equipment and taking data at remote sites, something that would serve him well about a decade afterwards. In 1912, two developments changed Eddington's scientific life. The first was that William Christie, the royal astronomer, took seriously ill, and feeling that he was unable to carry out his duties, Christie resigned his position. Selected to replace him was the well-regarded astronomer Frank Dyson. Dyson and Eddington shared a number of similar views, both on the best avenues of astronomical and astrophysical research, as well as with respect to how scientific inquiry was best done. As such, the two men became both trusted colleagues and close friends who would work closely together throughout both of the rest of their careers. The first result of this collaboration grew out of an eclipse expedition Dyson sent Eddington to oversee in Brazil. While the expedition was unsuccessful due to rain at the observing site, the process of having to set up 4 telescopes and figure out how to correct any errors between the differences of how the instruments measured the positions of objects in the sky, and by the way here, we're talking about fractions of a second of arc, led Eddington to develop a sort of a correction formula that could be applied to the instruments. There's this wonderful story that at one of the monthly dinners of the Royal Astronomical Society's Members Club, Dyson had been complaining that he needed a reliable way to calculate the corrections to his instruments at the Greenwich Royal Observatory. Eddington, overhearing the comment, turned over one of the menu cards and proceeded to write down the mathematical derivation and final formula for just such a correction, and then he just sort of nonchalantly handed it over to the somewhat nonplussed Astronomer Royal. The other development was that in the December of 1912, the Plumian Chair of Astronomy at Cambridge, George Darwin, son of the famous biologist, died rather suddenly, leaving the position unexpectedly vacant. On the strength of his observational work, Eddington was named to the position in 1913, though, to be honest, it was somewhat the junior appointment in astronomy at the university, and was supposed to be more focused on experimental work as opposed to Eddington's true strength of mathematical astrophysics. However, just a year later, the other professor at Cambridge, Robert Ball, who occupied the Lowndes Chair of Theoretical Astronomy, also died. This left Eddington sort of in charge of the entire astronomical program at the university, and he soon worked out with the administrators a way to combine the two positions, thus making him both the director of the Cambridge Observatory and freeing him to pursue any area of research he thought profitable. The following year, he was formally elected to the Royal Society. With these changes now in place, Eddington could be considered as an established member in what would be his permanent academic home for the next 30 years. If one thinks of the years spent at the Royal Observatory as his time as a journeyman in the field, Eddington would emerge as a true master of his discipline in his role as Plumian Professor of Astronomy and Director of the Observatory at Cambridge. In these two roles, he would be instrumental in both the fields of stellar structure and the emerging area of relativity theory developed by Einstein and other cosmologists. However, even as he participated in both of these sub-disciplines of astrophysics, his entry onto the main stage of astrophysical research was nearly derailed by Britain's entry into the Great War and his commitment to Quaker pacifism. During the years from 1913 to 1924, or perhaps even a bit later, it is clear that it is the valence values of Eddington's view of himself as a scientist and as a religious man that defined how he worked, what he undertook in the way of social causes, and how he understood the results of his inquiry. As we look into this period, what we will find is that Eddington tended to work on more than one project at a time, which can make disentangling his various efforts a bit tricky. In order to keep things understandable, what we will do is separate his work in stellar structure from his work in relativity in order to understand how each fit into his broader worldview and set of values. With this in mind, let's first look at the work he did in stellar structure. What should be understood here is that the period we will be describing will be prior to the work of a number of individuals, including somebody like Cecilia Payne-Gaspochin, who did work on spectral line analysis that eventually led to an understanding of the true composition of stars as being mostly made up of hydrogen and helium. During the period prior to that, there was a great deal of speculation as to what stars were and how they managed to actually produce light. Additionally, Eddington's work in this area can be understood to be very much in the theoretical camp, wherein he, along with a number of others, created mathematical models of objects beginning from various assumptions, and then worked to apply the laws of physics as they felt appropriate within the context of the types of physical systems the investigator would be interested in. To get a better sense of the actual context in which Eddington's work took place, what we need to do is go back a little ways, beginning with the work of Kelvin and Helmholtz and the idea of that slow gravitational collapse of a large mass of interstellar gas as the source of both star formation and the energy required for the light a star emitted. And that's something that we talked about in an earlier episode, so I won't go too much into it beyond what I've already said. So, starting from there, a number of individuals had taken the laws of thermodynamics and fluid dynamics as they applied to gases to create mathematical descriptions of how stars might balance the inward pull of gravity with some sort of outward pressure to maintain the star's size and shape in something known as hydrostatic equilibrium. I know that's a big fancy word, but just think of it this way. A star is pretty much a static looking thing, at least when you're observing it over a short period of time. What you've got to do is sort of come up with an explanation of why gravity doesn't pull all the stuff inward, or whatever's pushing the star out doesn't explode it out into space. That balance is what we call hydrostatic equilibrium. Now, this work had been taken up independently by the American astronomer Homer Lane and the Swiss physicist Jacob Robert Emden. And they developed a set of models for what are known as polytropic spheres that showed that the inward gravitational collapse could be balanced by the outward convection of matter. It's the same sort of thing that causes the hot water at the bottom of a pot on a stove to rise to the top when the bottom of the pot is heated by a burner or an element of some sort. Unfortunately, these models, while seeming to be correct in some ways, gave results that required a star to have to be giving off a whole lot more energy than was actually observed. Now, this work was then extended by Karl Schwarzschild, who happened to be related, interestingly, to Emden by marriage, and who recognized that whatever light was being generated in the hot interior of a star would interact with the matter, say, further out towards the edge of the star as it traveled through that matter, and thus it might exert an additional form of pressure. This radiation pressure, as it's called, would lower the amount of convection needed to balance the star's self-gravity, that idea that the star's own gravity is trying to pull it in. And this would be one of the places where Eddington would find an entry point into the discussion. The other had to do with attempts to understand what was going on with Cepheid variables. In 1913, Harlow Shapley, along with a few others, had suggested that the photometric data taken from Cepheid variables was not very well explained by the idea that what was being observed were that you had sort of two stars orbiting each other in what's known as an eclipsing binary. Instead, Shapley suggested that what was really going on in these Cepheids was that these were actually giant stars whose size was changing in a regularly pulsating fashion for reasons that he couldn't explain. This idea that the process might be something that would be modeled by the same kinds of tools that you could use for just understanding stars in general, i.e. the physical laws of thermodynamics and gas pressures, led Eddington to begin to build mathematical models based on an analogy with acoustic or sound waves traveling through a gas that would cause that gas to compress and rarefy. From these two entry points, Eddington began to work through a variety of models that made a couple of assumptions. The first assumption was that the source of energy production was not necessarily due to the contraction of a star, and the other was that the way in which light interacted with matter in the star was actually relatively unimportant. From these two assumptions, as well as a couple of other minor ones, he was able to derive two tremendously important results. The first was that Schwarzschild's radiation pressure was actually the dominant mechanism a star would use to balance the inward pull of gravity, with convection actually only playing a very small role. The second was that he could derive results from his pulsations theories that were fairly consistent with the observations of Cepheid variables within a certain range of masses. While the work was actually mathematically sound, dare I say brilliant, it engendered a good deal of critique from some of Eddington's colleagues, most notably that well-known and most respected of astrophysicists, James Jeans. Now, Jeans was about 5 years older than Eddington, and like Eddington, had worked his way through Cambridge's mathematical Tripos program and had emerged as a wrangler. He had held a professorship in applied mathematics at the University of Cambridge as a fellow there before taking a position at Princeton in the United States for about 5 years. Returning to Cambridge in 1910, Jeans taught for a couple of more years as a fellow at Cambridge there before retiring from his post. He had married a very wealthy woman and had decided to devote himself full-time to research, undistracted from the duties of teaching and university work. Like Eddington, he was mathematically talented, but unlike Eddington, he felt that all conclusions, whatever they were, and the assumptions that led to them should be arrived at through mathematical deduction rather than through speculation. In this, Jeans represented a long dominant view of how theoretical physics should be done that had stemmed probably from the time of William Thomson, known also as Lord Kelvin. While Jeans was originally intrigued by Eddington's work, especially with respect to extending Schwarzschild's radiation pressure idea, going so far as to offer helpful suggestions to bring Eddington's results even more in line with observations, he soon found Eddington's approach of just assuming certain physical processes to be unacceptable, and so he took to the meetings and journal pages of the Royal Astronomical Society to disagree, often rather vigorously, with his colleague. His issue was that he supported the convection model of Kelvin and Helmholtz, even in the face of a number of reasonable objections, and he felt that Eddington's assumption of some other energy source to produce the needed light to balance gravity was more than just a little ad hoc, and kind of represented what he thought of as sloppy thinking. History, of course, would prove Eddington to be right in the matter, but what I think I'd like to spend a bit of time on in this discussion is the difference between the two men's approaches and how Eddington's fundamental value that the best path forward was through seeking shaped his approach. In Eddington's initial papers, published in 1916 and 1917, one sees a willingness to consider new ideas, models, and mechanisms, things that just weren't sort of accepted earlier. The value of these new approaches was seen not in the fact that they produced a specific result, but in that they provided an avenue to move forward in asking questions and seeking answers to those questions. Whereas Jeans felt that only those results that could be mathematically proved and based on very, very sound and well understood physics, i.e. the idea of convection in this case, should be considered. Eddington felt that it was more important to be pushing the boundaries and trying new things in order to make scientific progress. This is clearly seen in the argument about what the source of energy for a star's light might actually be. For Jeans, since only energy production through slow gravitational collapse that converted potential energy into thermal energy could be mathematically derived, it was the only source that he thought could be considered. Eddington, in a very instrumentalist-style approach, said that since there were other possible mechanisms and that these mechanisms might produce energies in ways that were unknown until as they were unobserved, i.e., who really knew what went on in the middle of a star, he would build his models in the assumption that there was some source of energy that produced light in a relatively constant fashion, and then show mathematically that the pressure from that light would be the dominant mechanism to balance the inward pull of gravity. Far from being sloppy or wildly speculative, Eddington's approach allowed him to move beyond the constraints of a specific model that wasn't working very well to consider other possibilities. This, of course, required Eddington to make some assumptions about these processes, but his usual pathway was to show that when those parameters associated with his assumptions were varied, it turns out they didn't actually change the outcome of his mathematics in a significant way. For example, it turns out that it didn't much matter what his value for how much the light interacted with the matter, something known as opacity, varied. He basically got the same results no matter what that number actually turned out to be. From this, he claimed that the specifics of the physical characteristics of the model were significantly less important than the broader underlying processes he was suggesting. As a part of these early papers, Eddington did suggest that there was another form of energy production responsible, as he was able to show that the contraction model that Jeans was using would result in stellar lifetimes of actually less than 10 or 100,000 years, and that during that time, rotation rates for the sun would measurably increase in fairly short periods of time, something that just wasn't observed. The most notable of these ideas in terms of energy production that Eddington proposed, and it was one that prefigured the prediction and discovery of antimatter, was that there was some form of matter annihilation wherein the mass of positive and negative electrons, as he called them, that would collide would be converted into energy via special relativity's mass-energy relationship. While this turns out it was only, partially true, and his models didn't really require that mechanism to actually exist, it does really show Eddington's willingness to seek out new ideas in order to understand the processes and systems he was investigating through mathematical modeling. This attitude that scientific progress is best made not through only using a deductive practice of beginning with accepted and proven ideas, but rather that actually maybe the best way forward is to consider new explanations that open new pathways of investigation in a fashion that was entirely consistent with the Quaker idea of progressive revelation through the believer's interaction with that inward light all humans possessed. In this, religious truth was not only discovered and understood through the use of systematic theology based on and derived from dogmatic statements of belief. In fact, such dogmatic, and creedal formulations of faith would be rejected and replaced by a process of inward seeking wherein the follower would recognize that knowledge and understanding of the divine and a person's relationship with him would grow and change through experience. For Eddington, it is clear that his religious values both coincided with and informed his scientific values and processes, and vice versa, in a fundamentally integrated way that made the most important thing a person could do in any intellectual process be that of consistently and constantly seeking through a process of inquiry and examination of experience. In 1920, after spending time working in the field of relativity, Eddington would return to his stellar models to suggest that the energy source in the cores of stars would arise from the fusing of 4 hydrogen atoms into 1 helium atom, the latter having been shown in 1919 to have slightly less mass than its constituent components. Eddington reasoned that the pressures and temperatures he had calculated at the interiors of stars could well be enough to overcome the electrostatic repulsion between the protons in order to be fused together. As we have discussed in previous episodes, it would be more than a decade before first George Gamow and then a decade after that Hans Bethe would provide the key pieces to the puzzle that would allow for fusion in the cores of stars to be understood mathematically. In 1924, again after some time away from the subject, Eddington built on the work of a number of other astrophysicists to derive a relationship between the mass of a giant star and the amount of energy it gave off at all wavelengths of light, something known as the star's luminosity. He selected giant stars because it was thought that these were the only stars wherein the gas that made up the star was thought to obey the laws of physics pertaining to perfect gases, or ideal gases as they're sometimes called. When he plotted the known data for the masses and luminosities of well-characterized giant stars, he found an astonishing level of agreement of the data with his mathematically derived formula. He then decided to plot a number of lower mass dwarf stars, stars like our sun in a sense, on his graph to see how far they deviated away from his relationship in order to get a sense of what modifications to his model might be suggested by the data as a possible way forward, something very consistent with that idea that we just talked about. Much to his surprise, he found that these lower mass, lower luminosity stars also fit the curve very well, thus indicating that they too could be assumed to have, or at least to behave, as perfect gases. This was a really remarkable result, and it is now known as the mass-luminosity relationship, and it serves as one of the fundamental cornerstones of stellar astrophysics. As might be imagined, once again, Jeans found much to object to in Eddington's approach, but soon observations by Adams and Michelson at Mount Wilson began to provide results consistent with the predictions made by Eddington's models. In 1926, as would be his lifelong practice, Eddington would bring together his various researchers and results, along with those of his colleagues, even the ones that had initially disagreed with him or that he had disagreed with, and turned that all into a book titled The Internal Constitution of Stars that would become the standard work for some time on this topic. In that same year, he would also give a series of well-attended public lectures on the topics discussed in the book that showcased his, by this time, well-known ability to make accessible, difficult subject matter in a way that did not condescend to the listener nor trivialize the subject matter. As we've already mentioned, work on models of stellar structure weren't Eddington's only project during this time. While working on the papers that would mark his entry into the conversation about how stars remained in a stable configuration, he became aware of Einstein's work through correspondence with Willem de Sitter in the Netherlands. Now, to understand just how important this was, we need to build just a bit of context. As most of you probably know, in 1914, the Great European War began between the Entente powers of Russia, England, and France, along with other allies, most notably Serbia, on one side, and the Central Powers of Germany and Austria on the other. Now known as World War I, the initial expectation when the war broke out was that it would be quick and decisive, sort of a conflict along the lines of the 1870-1871 wars of German unification, including the Franco-Prussian War, that a lot of folks thought would be over in just a month or two. As such, the initial response of the British scientific community was a sincere hope that scientific collaboration would continue between the various combatant powers apart from the political difficulties. However, as word got out that as German troops marched through Belgium, a nation whose neutrality had been guaranteed by both England and Germany, and had in the process committed certain human rights atrocities and damaged a library of great cultural significance, the mood towards Germany as a whole, and the German scientific community specifically, began to turn sour. As the battlefront became a slaughterhouse and the war bogged down into trench warfare, the German use of poison gas ruptured whatever remaining goodwill existed. And so it was that as time progressed, more and more of the lines of scientific communication between the various scientific communities of researchers was ruptured. As this fracturing took place, most often with the active involvement of British scientists, there was a small minority who strongly advocated that it was essential that avenues of culture be maintained for a time when hostilities ended. Among those who held this position most strongly was Eddington, whose Quaker beliefs led him to the position that while nations may go to war, the animosity those nations feel should not be imposed necessarily on specific individuals. For instance, just because Germany and Britain were at war didn't mean that British scientists should necessarily hate German scientists or vice versa. This attitude arose out of his religious belief that within every human being was that God-given inward light that we've talked about, that each person could engage with and investigate, and in doing so, add a little more light to the world. Against this position were a number of Eddington's colleagues who could point to a letter that had been signed by a number of members of the German scientific community that defended German military action and the atrocities that had accompanied it. On his side, though, Eddington could point to another letter signed by a number of other German researchers, Einstein included, that denounced Germany's actions in the developing conflict and called for peace at the earliest possible time. Thus, when Einstein published the general theory of relativity in 1915 and early 1916, there were a number of barriers to it even making it out of the country and its scholarly journals, in other words, the scholarly journals of Germany, to other scientists in other combatant powers. However, as Eddington had worked very hard to maintain as many of his continental scientific contacts as he could, when de Sitter was able to get a hold of the relevant journals in which Einstein's papers were published, he was able to pass them, along with his own papers using the theory, to Eddington, who set out to understand them as completely as possible and then to disseminate that information to the English-speaking world. In 1918, Eddington published the first complete summary and explanation of the general theory of relativity in English, a work that became essential for understanding Einstein's breakthrough, as the Germans' own papers were not available and were oftentimes difficult to understand. In fact, there is a story that Eddington once is said to have mentioned Eddington's papers as the papers that were the best explanation of his theory of general relativity. Of course, as we've discussed in an earlier episode, Eddington would become the leader of an expedition to prove the prediction made by the theory of the amount of starlight, or the amount starlight would be bent by the sun's warping of spacetime. And you can go back to our episode on relativity to find a little more out about that. Now, we'll talk a bit about some of the details of this expedition in another context shortly, but planning for the expedition had begun as early as 1917 while the war was still going on. Eddington personally felt that the chance for a research team on one side of the war to prove the ideas of a scientist on the other side of that war was a profoundly important thing to do in the name of internationalism, and it aligned him with a number of activities other friends groups were doing to alleviate the suffering of non-combatants on both sides, even in the face of enormous opposition. As we've discussed, the idea for the expedition was to observe star positions of stars near the sun during the eclipse, in this case stars in the Hyades star cluster that makes up what we think of as a constellation of Taurus, or at least most of it, and then to observe if and how the positions shifted by taking photographs during totality and comparing them to pictures of the same region of the sky made at a time when the sun wasn't there. Eddington led one team to the island of Principe on behalf of the Royal Observatory, while another team traveled to a site in Brazil. The expedition was tentatively successful in providing evidence in support of Einstein's theory, though there were some problems with some of the equipment, especially with the team in South America. While there have been those who have questioned whether Eddington's early support of the theory of relativity biased him towards an examination and assessment of the data that was overly favorable to Einstein's prediction, a full examination of Eddington's reports to both the Royal Observatory and to the Royal Astronomical Society showed that he followed standard protocols of data analysis in arriving at his conclusions, and even went so far as to call for additional tests to be carried out during subsequent eclipses by independent teams to either confirm or refute his findings. The most important of these, of course, was the 1923 eclipse observations made in the South Pacific and Australia that provided strong confirmation of his results. In this way, Eddington provided an important test of general relativity in observing a newly predicted phenomenon. Moreover, over the course of the next several years, Eddington wrote extensively on both the mathematical framework of the theory as well as what it meant philosophically in ways that challenged older models of thinking. While we have talked a bit about the philosophical implications of relativity in our series of episodes on the philosophy of time, and I'd also like to make additional comments about the theory of relativity and the philosophical implications that it puts forward in a future episode, let me take just a couple of moments here to mention Eddington's ideas. Eddington, as he worked through Einstein's ideas and the mathematical framework that incorporated them, seems to have come to the conclusion that the fundamental discussion point was that physics was to be understood in terms of theory of measurement. In this, his understanding of relativity pushed him strongly towards both an instrumentalist and positivist perspective, wherein the scientist could only observe markings or pointer readings on a dial. In this view, relativity was a discussion of how different observers in different frames of reference would observe various pointers in making measurements of similar phenomena. From this, Eddington concluded in a strongly idealist fashion that the constructed understanding of the universe from these pointer readings arose from the mind as constrained by the data. From this, he concluded that the most important thing physics did was to understand the structure of things like space and time, And in doing so, he de-emphasized the role of matter, a choice he would be strongly criticized for given the place of chemistry in understanding how matter interacts. In other words, if you just look at it from a physics perspective, maybe the matter didn't matter so much. But if you took a broader view, if it included chemistry and later biology, it turns out that matter is actually pretty important. Perhaps the most startling and revealing of Eddington's thoughts, however, in this arena, might be subsumed under the heading of the illusion of solidity. Eddington pointed out that when we look at the world around us, we have this sense that it's this very solid and tangible thing, and that everybody sort of sees the same thing everybody else does. In other words, if you think about it, the seat you're sitting in, the walls you see, the floor you walk on, are all very real seeming, very solid, very substantial. And yet, it was clear that a very different picture was beginning to emerge that revealed such solidity to be something of an illusion created by our senses. By this point in time, physics was showing that matter was mostly empty space, with interactions between the tiny little pieces of matter being mediated by invisible and often undetected interaction fields. As an example, the seat you may be sitting on, or the floor or ground you're walking across right now, are, by and large, nothing, basically, literally nothing, with only 1 part in a billion, if even that, being occupied by matter. The forces you sense that hold you up to keep you from falling through the chair or the ground are nothing more than the electrostatic repulsion of the outermost electrons in your body being repelled by the outermost electrons of whatever surface that's supporting you. The pressure you experience when you push your hand against a wall is due to nothing more than the stretching and compressing of atomic bonds that invisibly hold the various tiny atoms that make everything up together. And if that isn't enough to blow your mind, and that's really quite an amazing thing to take into account, the other thing that, he points out is that beyond this is the understanding that arises from general relativity, that gravity itself isn't what it was thought to be. It doesn't arise from some force that one mass exerts on another mass, as Newton had once thought, but instead was rather due to a change in the structure of space-time created by mass so that objects moving in that space-time moved appropriately along lines of least action in that now curved structure. In his philosophical writings, we can see Eddington working to reimagine the world he lives in light of this new emerging picture of reality. Between 1920 and 1930, he will participate in not only the emerging mathematical understanding of what is now known as modern physics, but he'll be a powerful and consequential voice in the unfolding of a new philosophical understanding of the world that will forever banish the old assumptions of the ideas of classical physics to be replaced by the new ideas about what it means to construct models and theories. Again, his willingness to forge new understandings and embrace new philosophical frameworks rests in large part on his belief that the best path of intellectual and spiritual activity was to be constantly seeking and looking for ideas that move things forward and open up new avenues and opportunities of investigation. The rejection of formal dogmas and creeds found in the fundamental tenets of the Society of Friends was extended in Eddington to the practice of holding to scientific and mathematical frameworks loosely, with an understanding that through inquiry those ideas may be improved upon or even overturned. The final topic I'd like to spend just a bit of time on in this episode is Eddington's response towards the outbreak of hostilities in the Great War, as I think that it is that we can see how his religious and scientific values came together to guide his choices in ways that are both profound and instructive. As I begin this discussion, let me say that I understand that the topics that I'm going to discuss here are a source of much contention today, just as they were during the 4 years of the Great War. And so, in my comments here, it is not my goal to take a position on the various issues, as I think they are too complex and require a much deeper discussion than I'll be able to go into here. Rather, my hope is to faithfully share one scientist's response to war in the context of a discussion of his life, and then allow you, the listener, a chance to reflect on his situation and choices. Okay, with those caveats stated, let's look into this topic. As we've mentioned in both this episode and the previous one of the core beliefs of the Quakers was a commitment to pacifism and an unwillingness to engage in combat activities in a time of war. While this had always been a part of the Quaker faith, the Manchester Conference in 1895 and J.W. Graham's later writings on the topic had made the point that it wasn't enough for the Society of Friends and its members to be passive in this belief, but rather they had to engage in an active expression of the truth that all humans have the divine within them, and that warfare and violence is an affront to that inherent divinity. This meant that not only would the believer be expected to protest wars in some sense, but that they would refuse to fight and would act in ways that would seek to preserve life in the face of such violence. As you might imagine, this position was strongly tested as Britain decided to enter the Great War in 1914, and Quakers made their beliefs known in a number of ways, including volunteering for Red Cross teams and in efforts to provide aid and assistance for those non-combatants of any side of the conflict rather than fight. Their actions were often carried out at great risk and enormous personal cost, as British Quakers were often branded as traitors for providing aid to the enemy. Moreover, as recruitment drives to supply men needed to fight the war became more and more urgent, often mixed with propaganda that portrayed those who did not enlist to serve the realm in a time of existential crisis as being slackers or worse, those friends who chose to stand by their beliefs were ostracized and bullied. The only way to really fend off such attacks was to have one's position at home be identified as essential to the vital running of the country, something that required one to post a large placard that stated exactly what the exemption was for and why. These placards became in time something of marks of shame in the eyes of those who had lost loved ones on the French front or in Gallipoli. At the outbreak of the war, Cambridge had applied for exemptions for many of its faculty and staff, including Eddington. For Eddington, the exemption was based on the running of the Cambridge Observatory and the process and the value of collecting of data that observatory provided to the Royal Observatory. And that was kind of the reason that Cambridge put forward. However, for his part, Eddington had disagreed with this and had submitted a statement that he would not fight due to his religious beliefs. This, however, was ignored, as Cambridge didn't want to create an embarrassing public relations incident that would have been certainly reported in the various newspapers after war had started. And by the way, if you're interested in getting a broader picture of the series of decisions we're going to discuss and the social pressures that went along with those, I would recommend you listen to Dan Carlin's Blueprint for Armageddon series over at Hardcore History. He does a great job of talking about the various means the British government used to pressure young men into enlisting and then in creating a draft. For the first 2 years of the war, Eddington was able to sort of stay below the radar as it was, even though radar hadn't been invented by then, but you get the point. And he was able to do his work. But in 1916, after the disaster of the Somme, the enlistment numbers plunged to the point where it became difficult for Britain to live up to its manpower commitments. As such, the government instituted the first draft in the history of the nation, something seen by many as a betrayal of the idea that a liberal government would never interfere with the lives of its citizens at that level. It was really something that engendered an awful lot of debate and criticism, at least initially. With this done, it was now the case that those who had not enlisted on the basis of various objections would be called into the army, and thus review boards were established. Now, some of these objections would, of course, be for things that were still vital to the country's continued functioning, things like farming or munitions productions, that sort of thing. But others would fall under the status we now know as conscientious objectors, i.e. the idea that one's religious or philosophical beliefs precluded being able to take part in the conflict. Now, since there are a number of other resources available for those who are interested in researching this further, and by the way, Matthew Stanley's book, the one we mentioned in the last episode, has a really nice section on this. I will just say that the review boards were not very welcoming of the idea that anyone outside the most essential functions should be spared from the fighting. As such, what had been sort of a gradually worsening situation for those who held to their Quaker beliefs all of a sudden became significantly worse. Many were imprisoned and treated harshly, some even to the point of death. In Eddington's case, Cambridge's request for his exemption from military service was brought back up and was quickly denied. Cambridge appealed this, but this was also turned down, at which point Eddington himself expressed that he wished to be considered a conscientious objector. The review board took up this appeal for just a moment and again quickly denied it with what was and is a really fascinating reason. In their view, Eddington had applied for his initial exemption on the basis of his doing scientific work. This work was no longer deemed more necessary than having him fight on the front lines, and so it had been revoked. The conscientious objection claim on the basis of religious belief was then rejected because it was thought that one couldn't be both a scientist and a person of faith. You were either going to be excluded from military service on the basis of one thing or the other thing, but you couldn't do it, kind of have it in both ways, at least in terms of the way the review board saw it. Eddington then appealed this with the correct explanation that he hadn't, in fact, filed the first request, Cambridge had. Moreover, he said, he had submitted paperwork at that time saying that he wasn't going to fight on the basis of his faith, and that had been improperly ignored. Now, to be clear here, it's not that Eddington was being asked to be completely exempted from any sort of a role in the war effort at all. He was very clear in saying that he was willing to serve in those Red Cross units, as farm labor, or in any role not directly tied to the killing of other human beings. Also, it really should be emphasized what a courageous act of conviction this actually was in many ways, whether you agree with Eddington's stance or not. Eddington's own Friends congregation at Cambridge had had several of its members arrested and sentenced to either hard labor or harsh imprisonment, and at least one of those members had died on account of the mistreatment he had received as a result of these sentences. However, it was at this point that Eddington's status as being scientifically exempt from service was re-examined. Now, how this exactly came to pass is unknown, but most of what I've read suggests that Frank Dyson, the Astronomer Royal we talked about earlier, had pulled some strings further up in the government to get the case heard at a higher level than some local review board. This higher level board granted a 1-year continuation of Eddington's exemption in order to work on the pending eclipse expedition to Princeip, that one that we talked about that would end up proving the theory of general relativity. Eddington accepted this exemption, but with a written response that, in doing so, he was not giving up his status as a conscientious objector. So, a question that can come up as to why is there a change of heart to once again accepting an exemption status he had once rejected? Matthew Stanley puts forth the explanation that in participating in the eclipse expedition, Eddington saw himself as not just a scientist, but as a person engaging in the Quaker value of internationalism, in that participating in such an endeavor that would reach across borders, boundaries, and ideologies would be profoundly important. In this, he was placing himself well within the activities of other friends who worked to create a basis for rapprochement after the cessation of hostilities. In this, Eddington was prescient, in that the war would end before his 1-year deferment was over, and the eclipse mission was among the first scientific endeavors that began to build a bridge between the estranged scientific communities of the Central Powers and those of the Entente Powers. As we bring this episode to a close, allow me to apologize for the continuing delay in getting these episodes out. Though, for those of you who catch up to this later than in lifetime, I guess you won't notice that so much. With the conclusion of the semester and a bit of travel, I found it really hard to engage in the reading and research I need to do to get quality episodes put together. I can't honestly tell you whether this will continue, but I hope you'll hang in here with me as I try to work to get back to a more regular publication and production schedule. I have to say that some of this, of course, is a bit of burnout as we reach the end of our latest voyage, but my hope is that I'll, as we get into the new year, sort this all out. Once I get through the various biographical episodes I have planned, however, I'll probably take a bit of a publication break to get a bit of rest and then work to get ahead on my research for the next series. As I talked about in the introductory episode for the whole podcast, this might be a little bit of something along the lines of what Mike Duncan does, where he takes 4 or 5 weeks off to get ready for his next revolution. On a completely different note, for those of you in the San Diego area, I'm headed out your way after the first of the year. If you're interested, I'd love to meet up one evening for a couple of beers and some conversation if you guys are up for it. I'm still trying to figure out which night will be the best, but it'll either be January 6th, 7th, or 8th. If you'd like to join me or the group or whatever, maybe I'll be sitting there having a beer by myself, but if you'd like to join me, you can follow me on Twitter at Chad Davies or like the podcast Facebook page. You can just search on the Scientific Odyssey over there. And I'll be sure to post more information as to the wheres and whens of any gathering that we might have. Think of it as sort of a tweet up, I guess, is what the urban hip youth tend to call this, right? Finally, for everyone out there celebrating this holiday season, I wish each and every one of you a happy and peaceful celebration. Also, if I don't get to talk to you beforehand, I hope you have a happy New Year. Next week, I hope that we'll take a look at Eddington's later work, his interaction with another giant of astrophysics, and his writings on both science and religion. Until then, full sails on your journey.